This video is on finding related rates. Now we've seen how the chain rule can be used to find dy dx implicitly. So if you haven't watched the implicit differentiation video, please make sure and go watch that because implicit differentiation is going to be a huge chunk of related rates. So another important use of the chain rule is to find rates of change of two or more related variables that are changing with respect to time. I did an example where I showed you where something might be changing with respect to time. So this is what we're really going to be looking at when we talk about related rates. For example, say you're draining the water out of a conical tank. All right, here's our figure. We're draining the water out. The volume and the radius and the height, all these things, as it changes, as we drain water out, the amount of water is giving us different values for the volume, the radius, and the height. Okay, they're all a function of time, depending on if this is t equals 0, t equals 2, t equals 5. At different times, r is different, h is different, and the volume for sure is different. So we're looking at the equation v equals pi over 3 r squared h. That's the volume of a right circular cone, okay? So we can differentiate implicitly with respect to t to attain the related rate equation. So what we're going to do is we're going to say, okay, the derivative of v with respect to t is just dv dt. Okay? Here, the pi over 3 is a constant, so we can pull it out and say the derivative of r squared h. Since both of these are with respect to time, this is a product rule. So first times the derivative of the second with respect to time plus the second times the derivative of the first, 2r dr dt. So this is a related rate equation, right? You've got dv dt on this side, you've got dh dt, dr dt. So we can see how the rate of change of the volume changes with respect to how fast the h is changing and how fast the radius is changing. Now, what's good about this is if you know two of these, like I know that the water is leaving at a certain rate. That means that's a rate of change. That's the change in the volume, right? And I know if I have that, I can plug that in for dv dt. So sometimes we're given that kind of information. You'll see in just a second. So say we have this problem. Variable x and y are both functions of time and are related by the equation y equals x squared plus 3. So we want to find dy dt, and we're given when x equals 1, if when x equals 1, dx dt equals 2. So what are we talking about here? So we've got y equals x squared plus 3. So we take the derivative of both sides. So dy dt equals 2x dx dt. Now remember, if we're taking it with respect to time, we can't just do x because we're not doing it with respect to the same variable. So we have to have that dt. Plus derivative of 3 is still 0, no matter what the constant is, or what the variable is. So here we're asked to find dy dt when x equals 1 and dx dt equals 2. So this is easy. This is just plug and chug, right? So 2 times x equals 1 and dx dt equals 2. So dy dt equals 2 times 2 times 1, which is 4. So we're given now dy dt, assuming we're given extra information. Now, if you have any questions about how to do this, make sure you shoot me a reminder or ask a question in class.